external examiners ngayon?
Maganda, madali mamili ng external examiners. So the constraints are fewer. Plus, we also have broader reach. Maraming pwedeng manood.
Oo. Tapos,
dyan naman si Val.
oo.
Guys, question. Moderator.
Okay, everything is on live on YouTube now.
May question ako.
I hear noise from the background.
Guys, I have a question. Guys, question. Sino pwedeng sumagot? Si Dr. Garcia. Dr. Garcia.
Opo.
Pag dissertation, sino pwede ang mag-participate sa discussion?
Parang ano lang. May moderator naman yan eh. May host. Tapos may represent.
Sa panel.
Oo. Tsaka,
Panel muna, tapos kung may time.
Panel.
May kamay ko, Val. Val. Kamay ko. Yun.
Hindi, pero open. So panel yung ano.
Panel mauna, tapos pwedeng ilagay sa group chat yung iba pang questions. Tapos masahin natin. So panel yung ano. Panel mauna, tapos pwedeng ilagay sa group chat.
Bakit ganito? Wait lang. May
Nakamute ka, Jing. Nakamute ka, Jing.
I-mute na lang lahat tapos mag-raise hand na lang. Tapos
Okay.
si Jing o si Perry na yung bahala. So kagaya ng dati, no questions except Perry Katori. Okay? Tapos si Jing o si Perry na yung bahala.
Okay. Okay. All right. Please mute everybody.
Jing, please unmute, Jing.
Everybody.
Okay, yes. Hello.
Okay, Jing. Okay ka.
Okay, please mute everybody. If you could kindly please mute your phones.
Yung
or
phone,
your
yung cellphone, parang
Hello.
Okay, Jing. Okay ka.
Okay.
May nag-echo na yan.
Everybody kindly mute your phones. Ano ba to?
Mute all ako. Okay. Sige. Perry, mag-unmute ka, Perry. Sige.
Uy, nako. Ba't ako lumabas? Hi.
Hindi, okay lang. Okay ka pa. Nandiyan ka pa.
Oo, hindi. Pero, okay. Nakita ko yung mukha ko sa video.
Okay.
Wala nang echo?
Wala
na.
Okay, thank you. Sige. Let's begin. I'll just start with introducing. And could one of the readers be the moderator? Perry, could you be the moderator?
Okay.
Okay. Good afternoon, everyone. I'm very pleased to welcome you all to Alfred Abella's Ph.D. dissertation defense. Alfred comes to us from Tagum, Davao, and he has been with NIP much earlier than you think, because during high school, he has met Dr. Perry Esguerra as a Philippine Science High School student with Damien Dailisan. Okay, and when he entered the NIP, he applied in the video and image processing lab, where he showed interest in, as early on, he showed interest in waves, beginning with sound waves. And now, through BS, MS, and now his PhD. We will now talk about his interest on surface waves. So, Alfred Abella.
Moderator.
Moderator.
Terry, i-record ba to?
Yes, it's on YouTube, so it's being recorded live stream, and you can also record it on your own.
Okay, I'm also recording it.
Okay, so
okay.
Okay. So let me welcome everyone to Alfred Abella's dissertation defense. Following previous NIP practice, Alfred has 1 hour of relatively uninterrupted presentation, and after that 1 hour, there will be approximately one hour of open forum. So for the initial part of the open forum, the questions will be coming from the members of the panel. Meanwhile, the members of the audience can ask their questions by using the group chat. Okay, and I, as the moderator, will read those questions later during the defense. Okay, so if Alfred is ready, let me call on Alfred Abella to give his presentation.
So good afternoon, everyone. I am Alfred P. Abella, and I will be presenting my dissertation with the title Eulerian Vorticity on and Beneath Surface Waves Generated at the Liquid-Gas Interface. So here is an outline of my presentation. First, I will read the abstract, then a brief introduction discussing previous studies and the particular problems to be solved. Then I will discuss the linear water wave theory and analytical modeling, the spatiotemporal analysis of surface waves generating octopole vortices in a square domain, the Eulerian vorticity in octopole vortices generated by nonlinear surface waves, the Eulerian vorticity beneath rotating surface waves, and finally the conclusions. Here is the abstract. In this dissertation, I show the existence of the Eulerian vorticity on and beneath surface waves generated at the liquid-gas interface. The first case involves the generation of octopole vortices by a square waveguide. The octopole vortices, characterized by orbits of gyrating particles, are produced by rotating waves. These rotating waves are a superposition of phase-shifted oblique and orthogonal progressive waves. I modeled the motion of the advected particles using a technique which utilizes the superposition of velocity potentials and the analogy of the Eulerian vorticity contribution with the usual Stokes drift contribution generated by the surface waves. For the second case, I show the existence of the Eulerian vorticity by investigating the motion of submerged particles in vortex lattices beneath the liquid-gas interface or in the liquid bulk. The results are in good agreement with a previous theory which takes into account the additional Eulerian vorticity contribution. For the introduction, I will discuss particle control via surface waves in previous studies, the statement of the problem, and the novelty of the study. In previous papers involving floater particle control via surface waves, the clustering of the particles based on their wettability have been studied, such as this paper by Lukashuk and co-workers. We see here in A that initially the particles are scattered on the air-water interface, while in B, they are clustered and trapped along the nodes of the standing capillary surface waves as shown in C. The waves in C force the polystyrene particles to cluster and are produced on the water surface inside a vertically vibrated rectangular container. In another paper entitled Macroscale Assembly Directed by Liquid-Based Template by Chen and others, they studied liquid-based templated assembly for tissue engineering purposes. They were able to generate different patterns on the liquid-gas interface after also vertically shaking small polygonal containers. The waves generated by the shaking of the container produced these static patterns of tissue cultures. Large-scale counter-rotating eddies have also been generated inside a laboratory with the use of linear and nonlinear waves by Ponsman and his Australian group. The waves were produced by vertically oscillating cylindrical wave makers, which were half submerged on the air-water interface. And the nonlinear waves are oscillons, which force the central jet of the vortex pair to travel towards the wave maker in somewhat of a tractor beam effect. Also, using vertically oscillating cylindrical wave makers or plungers, configured as shown in the experiment setup, the Russian group of Filatov was able to produce vortex lattices as shown in A, using orthogonal and phase-shifted surface waves produced by the two plungers, and measure the corresponding vorticity at the air-water interface as shown in B. Note that this was published last 2016. The theoretical description of the phenomenon was discussed in their PRL paper with title Nonlinear Generation of Vorticity by Surface Waves, where they showed the vertical vorticity, that is, the z component of the vorticity or curl of the horizontal velocity field, to be this expression, where omega z bar is the vertical vorticity or the z component of the curl of the velocity field u. Psi is the phase shift between the wave makers. H1 and H2 are the amplitudes of the orthogonal standing waves. Omega is the wave angular frequency and K is the wave number. Now, a rebranding of this vortex lattice experiment was done by the same Australian group mentioned a while ago, now led by Francois. They named these vortices as wave-based liquid interface metamaterials and published their results in Nature Communications last 2017. They did not cite the experimental study of the Russian group I mentioned a while ago and discussed how these vortices consisted of nested and gyrating particles, only visible using high-speed and high-resolution video recording. They also added that these vortices are generated by rotating surface waves, since they knew a technique to image the surface waves with high spatial resolution at the liquid-gas interface, while the Russian group did not have a 3D wave imaging technique at that time. Another theoretical work by a part of the Russian group, led now by Parfenev, improved the description of the vorticity and generalized it for depths lower than at the interface. Notice that the spatial structure of the surface waves generating the eddy currents is similar to the ones obtained by the Australian group. Now, in the paper of Francois and company, wave-based liquid interface metamaterials, they mentioned the following. Note that the physics of the Lagrangian circular drift revealed here is intrinsically different from a recent Eulerian theory of vorticity generation on a surface perturbed by waves, which considers bulk viscosity as the essential ingredient of the mechanism. This recent Eulerian theory of vorticity generation pertained to in the text is the paper I showed a while ago by Filatov with the vertical vorticity for the vortex lattice given by this expression. In this reference, they missed the Stokes drift contribution, which therefore gives 2 plus square root of 2 for the vorticity prefactor at the interface instead of 1 plus square root of 2, which was corrected by Parfenev in their 2018 paper. Notice that if I plug in the value z equals 0 in the prefactor, e raised to 2kz plus square root of 2, e raised to kz square root of 2, we get the value 1 plus square root of 2. However, in the experiments of the Russian team, they found that this prefactor can reach up to 14 instead of 1 plus square root of 2. Sources of error include friction with the boundaries and capillary forces on the interface. Also note that based on the statement shown above, the Australian team of Francois does not accept the theory that the Russian team used to explain exactly the same phenomenon of vortex lattice generation. To clarify the issue further, in the paper of the Australian group, they computed the velocities of the particles using Euler equations with the implicit assumption, which means that the viscosity have been neglected. In their model, the linear wave velocity field UP can be solved using this implicit assumption, and this already provides the Stokes drift velocity contribution U sub d generated by the waves. The waves cause the particles to undergo fast gyrations, or the curling of the trajectories, and a slow drifting due to the Stokes drift velocity contribution while they propagate. Qualitatively, one can already recover the vortex lattice pattern from the velocity contribution UP. What they observed was that the Stokes drift contribution from UP was not enough to describe quantitatively the velocity of the slow drifting that they measured in their experiments. So they added another U sub d, but they adjusted the magnitude to match their experiments. So they used two contributions for the total velocity field. UP, which takes care of the fast gyrations, and the Stokes drift velocity, which translates the particles, and another Stokes drift-like contribution to match their experiments. Meanwhile, the Russian team computed the period averaged vertical vorticity of the vortex lattice using the Navier-Stokes equation, considering now the viscosity of the liquid. The vertical vorticity is the z component of the curl of the velocity field. They also found that two contributions to the vorticity. The first is the Stokes drift vorticity contribution, while the second is the Eulerian vorticity contribution owing to the viscosity of the liquid. Note that these two contributions have the same horizontal structure, that is, they look the same on the interface. Now, I can now then ask the following questions. First, can this additional Stokes drift-like contribution also be detected for a different vortex structure other than a vortex lattice, as was detected by the Australian team? And second, does this additional Stokes drift-like contribution from the Australian team actually correspond to the Eulerian vorticity contribution in the analytics of the Russian team, which was missed after neglecting the liquid bulk viscosity? So how can these questions be addressed? For the first one, I generate a different vortex structure, an octopole vortex, and compare it with how a vortex lattice is generated. I model this vortex structure and show if an additional contribution indeed improves experiment to model agreement. For the second question, I will prove the prediction of Parfenev by measuring the vorticity beneath the liquid-gas interface for a vortex lattice, instead of on the interface, so that I reduce possible sources of discrepancies observed in previous studies. One novelty of this study is that the motion of octopole vortices inside square wave makers has never been studied before. The Australian and Russian teams have previously generated the vortex lattice. Now I have generated an octopole vortex and obtained closed form expressions for the velocity field and waves advecting the particles. Second, the vorticity beneath the rotating surface waves, which generate the vortex lattices, has never been examined before. That is, I will show experimentally that vorticity generation by surface waves requires the Eulerian contribution owing to the liquid viscosity. Now I'll go through the linear water wave theory and analytical modeling, including the governing equations and boundary conditions, the solutions to the boundary value problem, and the modeling of rotating surface waves and vortex lattices. A diagram for the boundary value problem specification for periodic water waves is shown here. We make use of the Laplace equation, where phi is the velocity potential and the velocity field u is del of phi. To simplify the analysis, we will consider for now a wave that propagates along the horizontal x-axis with heights measured along the vertical z-axis. The bottom boundary condition imposes zero flow through the rigid bottom. The kinematic free surface boundary condition relates changes in the surface displacement to the potential components of the flow. The dynamic free surface boundary condition expresses momentum balance at the surface z equals eta. And the periodic lateral boundary condition imposes wave periodicity in space and time. Now, one solution of the Laplace equation, given the boundary conditions, is the velocity potential for a standing surface wave. Given this expression for phi, we can also write another solution given by this expression. And this differs from the previous form of phi above in that the x and t phase terms are shifted by pi over 2. Now, subtracting this to the original form, we get another solution. We can then again shift the overall phase by pi over 2 so that we get this velocity potential for a progressive surface wave propagating towards the positive x direction, where L is the trough to crest height, D is the liquid depth, K is the wave number, and omega is the wave angular frequency. We now proceed with the modeling of the rotating surface waves and vortex lattices that I showed a while ago. The experiment set up to produce the vortex lattice involves two wave makers, which produce waves that propagate along the x and y axis. This pair of waves should have a phase difference of pi over 2. These wave makers are placed against the walls of the rectangular water tank so that waves are also produced due to wall reflections. We already know the velocity potential for a progressive surface wave, and now we can write the velocity potential for the superposition of orthogonal progressive surface waves with phase shift along the y-axis as this. And simplifying, we get this expression for the velocity potential producing the vortex lattice. We can then get the velocity field advecting the particles to form the vortex lattice, since UP equals grad of phi and the phase shift psi equals pi over 2. The subscript P denotes the inviscid potential assumption. The velocity field generating a vortex lattice is then given by this expression. Note that this is linear with respect to the crest to crest wave amplitude capital L. Now, integrating this velocity field in time generates the vortex lattice. Shown here is an example of a 2x2 lattice from the paper of the Australian group. Now, to generate an n by n lattice, we must set the wavelength lambda equal to 2s over n, where s is the side length of the square domain where the lattice is generated. We can then get k from lambda, and we can get the wave angular frequency by plugging in k to the dispersion relation for the surface waves, where omega is equal to 2 pi f, the surface tension is sigma, the density is rho, and the water depth is d. F is the angular frequency set in the frequency generator. This is my own render of the particle trajectories for a 3x3 vortex lattice generated in MATLAB. You can clearly see that a vortex cell consists of nested and gyrating particles. They also drift from their starting positions, which are the black dots as indicated in the figures. Now, to model the rotating surface waves which produce these particle tracks, we use the recasted form of the dynamic free surface boundary condition to make use of the velocity field for the vortex lattice. Substituting and simplifying to retain terms up to order eta, we have this expression for the surface wave heights with the following contributions. And this is a visualization of the Australian team for the surface waves. They said that these waves are rotating since the wave crests and troughs change positions in contrast to standing waves. The rotation of the waves provides the momentum for the particles to drift within the vortex lattice cells. To visualize what happens during experiments, I made my own visualizations of the rotating waves and the vortex lattice. If we randomly place floating particles on the liquid surface, which trace the motion of the fluid particles, we will see something like this. Notice how the waves are rotating, but the motion of the tracks of the particles are not so obvious. To visualize the vortex lattice, we must keep track of the path of the particles as shown here. Now we can see the gyrations and drifting of the particles as they are advected by the rotating waves. Here is another visualization without the waves. Now looking at this vortex cell, if we focus our attention to specific regions through which the fluid flows in time, then we are looking at an Eulerian view of the flow field and we see closed orbits, just like this. On the other hand, if we follow the motion of a specific floating particle or fluid parcel in time, then we are looking at a Lagrangian view of the flow field and we see something like this. In the Eulerian view of the flow, there is no mass transport, and the particles form closed orbits after one period. While in the Lagrangian view, there is mass transport, and the particles form open orbits after one period. This mass transport distance is called the Stokes drift. We can also obtain the Stokes drift velocity U sub d for a particle oscillating in the neighborhood of its original position. We can write its instantaneous velocity in terms of the velocity at its original position, where delta x is as given. Now getting the period average value of the velocity, we get the following equation. The term on the left is the average Lagrangian flow velocity or the mass transport velocity. The first term on the right is the Eulerian velocity contribution, and the last term is the Stokes drift velocity contribution U sub d. Now, if we use the previously obtained linear wave potential velocity field for the vortex lattice and substitute it to the equation for the mass transport velocity, we find that the Eulerian velocity contribution due to UP is 0, and only the Stokes drift from UP contributes to the overall transport of a particle from its initial position. Even though the Stokes drift from UP contributes to the overall transport of a particle, Francois and his co-workers noticed that this contribution was not enough to match the experiment results. They had to add another Stokes drift-like contribution, but with the velocity magnitude adjusted. They calculated U sub d from UP to get this, and its amplitude is given by B. They adjusted B, but they did not describe the exact method and parameters they used to compare and adjust this quantity to match their experiments. To summarize, in the paper of the Australian team, they modeled the velocity using Euler equations with implicit assumption, so that there is an additional Stokes drift-like contribution to match the experiments, and a potential velocity which already includes the Stokes drift contribution from the linear wave motion. Now, if I compare these two equations, I believe that the additional Stokes drift-like contribution that they added to match their experiments correspond to the Eulerian velocity contribution, but not due to the waves. In fact, based on the results of the Russian group, the period average vertical vorticity considering the liquid bulk viscosity involves a Stokes drift contribution and an Eulerian vorticity contribution owing to the viscosity, which has the same horizontal structure as the Stokes drift. In my experiments, I will show that this additional contribution exists, for an octupole vortex. Also, contrary to the statements of the Australian team regarding vorticity generation of their vortex lattices being different from the theory which takes into account the liquid viscosity, I will show experimentally that the Eulerian contribution, owing to the viscosity, is indeed necessary. Now, in this part, I will answer the question, can the additional Stokes drift-like contribution also be detected for a different vortex structure other than a vortex lattice? And to answer this question, I generate a different vortex structure, specifically an octupole vortex, and compare it with how a vortex lattice is generated. In the paper of the group of Chen, I showed a while ago that they implemented liquid-based templated assembly for tissue engineering. Here is their setup. They place the cultures inside a 1 cm by 1 cm square cross-section vessel that is vertically shaken so that surface waves are produced. Now observe that they have also produced similar vortex lattices, but particles cluster along the separattices and do not gyrate and drift. Standing waves and not rotating waves produce these. Another pattern that they produced is this. It has 8 separattices shown through the green lines. And aside from horizontal and vertical lines, diagonal lines are also present, in contrast to the vortex lattice. The question is, can I get a similar pattern with 8 separattices where the particles gyrate and drift instead of being clustered as shown, since the particles gyrate and drift for the vortex lattice of the Australian and Russian teams. That is, there is mass transport. And then I ask another question. Can I model this pattern using the same technique described previously? To do this, I used a different setup to produce the waves. And here are the part specifications. A camera is placed above the entire setup. An acrylic tank is filled with water up to some height. A subwoofer speaker is controlled using a function generator, and its diaphragm is attached through aluminum rod attachments towards a wave maker. The wave maker is an open square with edges made of acrylic cylinders. The wave maker is half submerged on the liquid-gas interface, so that as the speaker diaphragm vertically oscillates, it also oscillates, producing the surface waves inside its square domain. Tracer particles were used to track the motion of the liquid particles, and LEDs are placed below the tank for illumination. This is a video of the actual setup and operation, where this is the wave maker, a light diffuser for the LEDs, and here is the speaker. The resulting pattern of the trajectories of the particles using a frequency that produces an octupole vortex is this. This is a top view of the liquid-gas interface inside the square wavemaker domain. Notice that if we zoom in on the upper left vortex cells, we see that the particles gyrate while drifting, similar to that for the vortex lattice. Now, to generate this pattern, we measure the wavemaker side length S, compute the capillary length L sub c to consider the meniscus thickness, and compute the effective vortex side length as L effective equals S minus 2LC. The wave number is K equals N pi over L effective, where N equals 5. And we plug in the value of K to the dispersion relation using the following specifications for the liquid used, which is water. The water depth D equals 53 millimeters. A surface tension sigma equals 7 millinewtons per meter. And the density is rho equals 1000 kilograms per cubic meter. Omega is 2 pi f, so that we set the frequency generator to f equal to 7 hertz for this case. So the answer for the previous question before is yes. And the particles drift towards the center of the wavemaker edge instead of moving away from it. Also, they move away from the corners. Now, is the drifting caused by rotating waves similar with the vortex lattice. To image the waves, I use the free surface synthetic serine or FSS technique. Here is a similar setup before with a minor change. Here are the steps for the FSS technique discussed in the paper indicated. The camera is placed above the setup as before, and now we place a random dot pattern below the tank. This is a top view of the interface inside the square wave maker domain, and we can see the random dot pattern. The pattern is printed on an A3 sized paper with dots of 1 millimeter diameter each. We then record videos with and without surface waves, and a code should be implemented which corrects camera distortions and sorts the images. I use the PIV Lab software to compute for the deformation vectors of the random dot pattern. Here is the PIV Lab software used in conducting particle image velocimetry in MATLAB. As shown here, the green quivers are the dot deformation vectors caused by the lensing effect of the wave crests and troughs. I can then compute the surface height gradients for this case along the x-axis using the following relationships and integrate along x and y to get the surface wave heights. The resulting wave heights using these vectors is this. Notice that the wave crests, or the highest portions of the waves, and troughs, or the lowest portions of the waves, move out towards the edges and move in from the corners to the center. A different view of the waves is shown here. Here, A shows waves at one video frame with half the wavelength as the scale. B shows the average temporal spectrum of the waves. The inset is a result of using a filtering technique which only shows the value of the average temporal spectrum around the forcing frequency f equals 7 Hz for all space. With this, we see that the wave nodes correspond to eyes of the octopole vortex. In C, the wave crest is tracked for the corner to the edge, from the corner to the edge for one wave period T. And D shows the track of such wave crest in C, as directed by the arrows and the black dashed line. And it also shows the visited sites of the crests and in red dots and the troughs in blue dots. From all of these observations, we can say that the waves are also rotating, and this gives the necessary momentum so that the particles move in towards the edges and move out from the corners, forming the octopole vortex cells. Now, I want to know what wave components make up these rotating waves. So I want to isolate them based on their directionality. First, we get a line scan profile across X and stack with profiles from other times, as shown here in A. Next, we get the 2D Fourier transform, as shown in B, and obtain only the right and left moving waves by covering the second and fourth quadrants and first and third quadrants, respectively, as shown in D. To reconstruct the 2D waves at a specific time, get the inverse 2D Fourier transform, as shown in C, and repeat the entire process for all line scan profiles across X. The resulting restacked profiles after inverse Fourier transformation are shown in E for the right moving waves and in F for the left moving waves. A similar process can be done to get the upward and downward moving waves. Just stack the y-axis profiles instead. Notice that the right and left moving waves have components coming from the corners. To show these component waves, the same process can be done to both left, right, and upward, downward propagating waves, but stacking line scan profiles across the y-axis and x-axis respectively. And these are the resulting wave components. Oblique waves is seen to be coming from the corners based on these results. So far, the results suggest that the octopole vortex consists of gyrating and drifting particles similar to that observed in the vortex lattice. These two vortex patterns are both generated by rotating surface waves. And for the vortex lattice, the rotating waves are generated due to the superposition of right-left and upward-downward moving waves, but have a phase difference between them of pi/2. Purely right-left and upward-downward progressive edge waves and oblique waves from the corners exist to generate the rotating waves for the octopole vortex. But what is the phase relationship between these edge and oblique waves? To find out the phase relationship between the oblique and edge waves, I constructed a modified setup wherein only one edge of the square wave maker is oscillating. The diffusing light imaging or DLI technique is used to image the waves, which uses milk water solution as liquid, and calibration is done to relate the wave heights to camera detected light intensity from the LEDs. For time t, these are the waves produced by the single oscillating edge. But at a later time t plus 1/4 of the wave period, or equivalently a phase delay of pi/2, the straight edge waves are modified to this pattern in B. If I do the same wave isolation component technique described a while ago for these waves, we see that oblique waves exist after a phase delay of pi/2 with respect to the edge waves shown in A. Now, if I rotate the instantaneous wave heights by 90 degrees, 180 degrees, and 270 degrees, and add to the original, and do the same filtering technique of the forcing frequency as before, then we get this pattern for the superposition of waves from the single edge wave maker, which is very similar to the pattern shown a while ago when the entire square wave maker was oscillating. Now that I know the component waves, I can now model the rotating waves and the octopole vortex. The velocity potential for a progressive surface wave is given by this expression. Therefore, for the edge waves, I set a similar form for the potential phi sub e. The four edge waves come from the left, right, up, and down sides of the square wave maker, and we just replace x with y for the up and down edge waves. For the oblique waves coming from the corners, we write the potentials phi sub o as given, with the phase shift small phi equals pi/2, and theta, which indicates the rotation about the x-axis to be plus minus 45 degrees. Then the total velocity potential after adding up all 8 components is given by this expression, where the variables are as indicated. This closed form expression looks manageable, and since the velocity field UP equals the gradient of the velocity potential, I can get the following expression for UP. A while ago, I mentioned that an additional Eulerian contribution owing to the liquid viscosity possibly exists, which should be added to the mass transport velocity. If I let this have the same horizontal structure as the Stokes drift U sub d, then I have to solve for U sub d given by this expression, and I get the following x and y components for U sub d, where a equals x and b equals y for the x component, and a equals y, b equals x for the y component in this expression. The result of integrating the total velocity u with alpha equals 1 using a fourth order Runge-Kutta integration scheme is shown here. The octopole vortex can be observed, and zooming in on a portion shows the gyrations, while the particles drift from their initial positions, shown as the small black dots. Here we see an animation showing the tracks of the particles forming the octopole structure. A zoom in of the upper left portion of the square domain is also shown below, and a 3D render of the tracks close to the eye of a vortex cell, which clearly shows the particle gyrations. To model the surface waves, we again make use of the dynamic free surface boundary condition using UP and linearization to obtain a closed form expression of the wave height eta. And shown in A are the waves at one time step, and in B, the visited sites of the crests and troughs. Notice that the pattern is very similar to the one we got before for the superposition of waves from a single wave maker. Here is a 3D render of the surface waves. The waves indeed move towards the edges and out from the corners of the square wave maker. Here is another one showing the particle tracks with the waves. With these results, I have shown that I can model the octopole vortex and the rotating surface waves which generate them. Now in this section, we look at the second answer to the first question, where now I model the octopole vortex structure and show if an additional contribution indeed improves experiment to model agreement. That is, I optimize alpha with U equals alpha U sub D plus UP. I modify the experiment setup for this part. I want to measure the motion of the waves and the tracer particles, but I cannot measure these two simultaneously. C and D shows the random dot pattern with and without the waves for the FSSS technique. I used polyamide spherical particles with density which closely matches that of water. A black cardboard is placed below the cover to cover the dot pattern and make the white particles visible. I also used a corner LED illumination to increase contrast. The measured waves for a time step is shown in A. B and C shows the wave heights in time, which gives the highest eta for the corresponding forcing amplitudes which produce these waves. Now, increasing the forcing amplitude increases the wave nonlinearity. The crest to trough wave height asymmetry can also be observed, characteristic of nonlinear waves. Due to this asymmetry and the difference in peak heights, describing the wave in terms of the mean wave steepness would not be ideal. Instead, I quantified the nonlinearity through this quantity beta equals 1 minus A tilde sub F over A tilde sub T, with A tilde sub F as this integral, which is the same filtering integral I've used before around the forcing frequency F, while A tilde T is the integral over the entire average temporal spectrum. I used 4 forcing amplitudes with the corresponding values of beta, and here are sample average temporal spectra from which the beta values are computed from. Now, beta increases as the wave nonlinearity increases, and the contribution of the forcing frequency to the overall spectrum decreases. The non-dimensional wave steepness, K eta, equals 0.12, greater than 0.1 for the lowest value of beta. K eta equals 0.1 is the typical threshold for linear waves. Using PIV lab, I measured the horizontal velocities, U of the tracer particles placed on the air-water interface after measuring the waves. The vertical vorticity is then computed as the curl of U. Here are the results for the average velocities in quiver plots and average vorticities in color map for the 4 beta values. The vorticity amplitude increases from 0.7 to 2 for the highest beta. The vorticities weaken near the walls due to friction, so I zero padded these regions for each. And these are the padded versions. I then proceed by optimizing alpha for the analytical model velocity u, where I ran alpha from 0 to 100 in steps of 0.1. I then compare the analytical vorticities with the experiment by separately minimizing two quantities. For the first one, I minimized the peak of the distribution of the difference between the experiment and model vorticities. To do this, compute the 2D vorticity difference, delta omega, then obtain the distribution of delta omega, which is denoted by this. And lastly, plot alpha versus the distribution p of delta omega. The other quantity is this, which is the spatial average of the 2D vorticity difference. Shown here in the figures are plots of these two quantities versus the velocity prefactor alpha. We see that for all levels of nonlinearity beta, particular values of alpha do exist, which minimize these two quantities. And we denote these optimal values as alpha naught. Here are the example modeling results using the corresponding optimal prefactor values for beta equals 0.378 and beta equals 0.396. For alpha equals 0, meaning no Eulerian contribution, the peak omega reaches to only about 0.5 for beta equals 0.396, while it reaches 1.2 to 1.3 with the Eulerian contribution, which is much closer to the experiment peak omega approximately 2. Also, for alpha equals 0, vorticity holes are visible with similar smaller vortices close to the center. For non-zero alpha, the holes and smaller vortices become less evident in comparison to the larger vortices, which follow the experiments. Here is a more comprehensive plot of the wave nonlinearity level beta versus the optimal velocity prefactor alpha naught. The optimal value alpha naught decreases as the level of nonlinearity beta increases. The scaling parameter alpha naught remains to be greater than 1. And for the case of vortex lattices, the factor alpha, which rescales the Eulerian contribution according to the analytical prediction of Parfenev et al., is alpha naught equals square root of 2, or about 1.4, at the interface z equals 0. This value is very close to the factors obtained for the highest wave nonlinearity level, beta equals 0.396 for the octopole vortex. The values for the no-pad cases are alpha naught equals 1.4 and 1.5 using the two methods, while alpha naught equals 1.7 and 1.8 for the padded cases. Thus, the modeling requires the existence of the Eulerian contribution alpha ud to qualitatively describe the octopole vortices. For this last part, I will answer the following question. Does the additional contribution correspond to the Eulerian contribution, which was missed after neglecting the liquid bulk viscosity? The answer is to prove the prediction of Parfenev by measuring the vorticity beneath the liquid gas interface for a vortex lattice. Let me recall the analytical prediction of the Russian group regarding vorticity generation by the surface waves. They found that for the vortex lattice, two vorticity contributions are present, namely the Stokes drift and Eulerian vorticity contributions. Now, how are these two contributions generated? As explained a while ago, the Stokes drift contribution is determined solely by the potential wave flow in the inviscid assumption. The Eulerian contribution is 0, assuming potential flow. The viscosity of the fluid is what generates the Eulerian contribution. It violates the potential approximation in a description of the surface waves and leads to the appearance of a non-zero horizontal vorticity concentrated in a thin viscous sublayer near the interface. This horizontal vorticity is tilted due to the surface wave crests and troughs and thus contributes to the vertical vorticity observed in vortex lattices. Finally, this Eulerian contribution spreads to the bulk through viscous diffusion. What I did was generate the vortex lattice and attempt to show experimentally that this Eulerian contribution owing to the liquid viscosity indeed exists, but below the surface waves. The Russian group have already done experiments at the liquid-gas interface and have shown that the p-factor 1 plus square root of 2 reaches much larger values due to contamination on the interface, capillary effects between particles, and wall friction. So I decided to measure the vorticity beneath the surface. Shown here is my experiment set up to generate the vortex lattice. A camera is placed above. An acrylic tank with indicated dimensions is filled with the liquid. The shakers are two woofer speakers controlled by a function generator. The light sources are bottom LEDs for the imaging of the waves, corner LEDs for the vortices at the interface, and a 532 nanometer diode laser for the vortices below the interface. The wave makers are half-submerged acrylic cylinders with diameter of 10 millimeters, and I use two pairs. One pair with lengths L equals 100, and the other pair is L equals 110 millimeters. Two types of tracer particles were used. Polyamide spherical particles for interface measurements, and slightly more dense but smaller silver-coated hollow glass spheres for below the interface measurements. Lastly, the liquid used is 40% by volume glycerol water solution at a depth of 20 millimeters with the following properties. Rho is the density, sigma is the surface tension, nu is the kinematic viscosity, and n is the index of refraction. To measure the waves, only the dot pattern is placed below the tank and the bottom LED is on. To generate n by n vortex cells for the lattice, we must set lambda equals 2 times L effective over n, where L effective is equal to the length of the wave maker L plus 2 times 1 millimeter minus L sub c, where L sub c is the capillary length equal to square root of sigma, the surface tension, over rho times g, the gravitational acceleration. For the two pairs of wave makers used in my experiments, the forcing frequencies and wave numbers are the following. One wave maker for each pair is delayed by pi over 2 phase during the experiments so that we generate the vortex lattice. The result of the surface wave 3D visualization using FSSS is shown here. Notice the similarity of the movement of the waves for my experiments in comparison to the waves of the Australian team. Thus, in my experiments, rotating waves are indeed generated by orthogonal and phase-shifted standing waves. Now the question is, do these rotating waves generate the vortex lattice in the interface as expected? Shown here is a zoomed-in view of the liquid-gas interface. PSP, or the polyamide spherical particles, were used as spacers. The blue box is the region of interest for particle image velocimetry using PIV lab. This is how the tracer particles move. The vortex lattice is not readily visible. But if we stack the image frames every time step, this is what we see. In the video and the image shown below, the video frames were stacked to visualize the trajectories. From this, I can say that rotating waves do generate the vortex lattice. I focused on measurements in the center vortex cell to reduce wall friction effects. Now, using PIV lab again, I conduct particle image velocimetry using an integration window size of 64 by 64 pixels And the resulting instantaneous velocity vectors are as shown. Now, to be able to say that the vortices I am producing is exactly similar with what the Australian group was able to produce, I checked whether the particles also gyrate while drifting. Using the instantaneous velocities of the center vortex cell, I employ a step-by-step integration scheme using a fourth-order Runge-Kutta. And to get finer steps in space, I interpolate the velocity values at the current location after the previous time step before proceeding with the integration. And this is the resulting image for 23 wave periods. The inset shows us that the particles indeed gyrate while drifting inside the cells of a vortex lattice. With all these results, I can say that I have produced rotating surface waves and the vortex lattice at the interface. Now I'll describe the imaging of the vortices in the liquid bulk or below the liquid-gas interface. Here is a side view of the experiment setup showing the wave maker pair and the suspended silver-coated hollow glass spheres. In this image, the tank filled with the liquid solution is shown, and the direction of the laser sheet illumination for the particle image velocimetry is indicated by the green arrow. This is an enhanced version of the same image to show the mount connected to the wave maker and the speaker. These parts were shown before in this part of the setup schematic diagram. A side view of the experiment operation is shown here. I focused on measurements in the center vortex cell and in the liquid bulk to neglect the capillary and surface film effects. Notice how the waves are induced due to the vertical motion of the wave makers. Here is a top view of the center vortex cell for the wave maker length L equals 100 millimeters. For the depth, Z equals 3 millimeters. And Z equals 7 millimeters. I want to note that neither the Australian nor the Russian team has imaged these vortex cells beneath the interface yet. The measured velocities were also used to reconstruct the particle trajectories, as shown here. Shown in H are sample radial profiles of the average velocity magnitudes for depths 3, 7, and 13 millimeters below the interface. This means that the velocity increases from the eye of the vortex cell up to the separatrix. Note that this is consistent with the observations of the Australian team for the velocity profile of a vortex cell at the interface. Now, to confirm the predictions of Parfenev, which is given by this expression, the mean vorticities are computed from the PIV velocities using this expression. Omega equals the curl of the velocity field, and we get the Z component. And doing that, we get here the vorticity for Z equals 3 millimeters and Z equals 5 millimeters for L equals 100 millimeters. The absolute value of the vorticities have already been obtained. Now, to eliminate the dependence of lambda of xy, since I cannot measure the wave simultaneously with the PIV, and I wanted to focus on the non-dimensional scaling p-factor, e raised to 2kz plus square root of 2, e raised to kz square root of 2, a reference two-dimensional mean vorticity, omega sub ref, average over a fixed period is set, which is closest to the interface. The other vorticities at other liquid depths Z are denoted as omega sub Z. I then computed the ratio omega sub ref over omega sub Z, which is a two-dimensional image, and got its distribution. For L equals 100 millimeters, the omega reference was measured at Z equals 3 millimeters below the interface. And here are the normalized density curves for the vorticity ratio distributions for the indicated depths. I obtained the peak of the distributions and the width at half prominence, or the maximum height. After which, I then computed the analytical omega sub ref over omega sub z values using the equation given, and compared the results to the peaks of the distributions. Recall that the first term is the Stokes drift contribution, and the second term is the Eulerian contribution owing to the liquid viscosity. Here are the results for L equals 100 millimeters and L equals 110 millimeters. The black dots are the averages of the density curve peaks using 3 fixed durations for every z. For L equals 100 millimeters, the fixed durations span 27 periods from 195, 205, and 215 of the wave period after the start of forcing. And for L equals 110 millimeters, the fixed duration span 30 periods from 180, 189, and 198 of the wave period after the start of forcing. The lower error bars are the standard deviations of the peaks of the 3 spans. The upper error bars indicate half of the peak width of the distribution for 27 periods for L equals 100 millimeters and for 30 periods for the given duration for L equals 110 millimeters. The characteristic time of vorticity evolution is 1/2 nu k squared, where nu is the kinematic viscosity and k is the wave number. And these times are 13 periods and 16 periods for L equals 100 and 110 millimeters respectively. So we are in the steady state. The vorticity ratio distribution peaks are closer and lean towards analytical values with the Eulerian vorticity contribution. This suggests that the vorticity decays much slowly with depth than when the Eulerian contribution is neglected. Now, obtaining the distribution of the vorticity ratios instead of just computing the average value over all space is more appropriate, since this does not assume self-similar scaling of the ratios throughout all the pixels of the two-dimensional image, since the shapes of the density curves differ from each other. To further quantify the closeness of the experiment density curve peaks with the analytical values, I computed the percentile rank deviations. The percentile rank P gives the percentage of the number of data points over all the data that has a value that is less than or equal to a desired data value. Thus, it gives an idea of the location of that number on the distribution. I denote the percentile rank of the analytical vorticity ratio with the Eulerian contribution with respect to the data as P sub E, while P sub N for the analytical vorticity ratio without the Eulerian contribution. Then delta P sub E equals P minus PE, the absolute value, and delta P sub N equals the absolute value of P minus P sub N, are the corresponding percentile rank deviations. A lower percentile rank deviation suggests that the density curve peak value is close to the analytical value. Here are the resulting percentile rank deviations for L equals 100 millimeters and L equals 110 millimeters. We see that for all samples, delta P sub E is less than delta P sub N. This suggests that the vorticity ratio peaks are closer and lean towards the analytical values with the Eulerian contribution. The Eulerian contribution, owing to the liquid viscosity, is indeed necessary to quantitatively describe the generation of vortex lattices by surface waves. Now to conclude, in this dissertation, I have addressed the following questions. Can the additional Stokes drift-like contribution also be detected for a different vortex structure other than a vortex lattice? The answer is yes. And I have characterized a different vortex structure, which is the octopole vortex. It is generated by rotating waves, which is a superposition of phase-shifted, oblique, and edge waves. I modeled this vortex structure and showed that an additional contribution indeed improves experiment-to-model agreement. Now, does this additional contribution correspond to the Eulerian vorticity contribution, which was missed after neglecting the liquid bulk viscosity? I have shown that this additional contribution closely corresponds to the Eulerian vorticity contribution, as predicted by Parfeniev. by measuring the vorticity beneath the liquid gas interface for vortex lattice. Here are the relevant contributions of my dissertation. To my knowledge, there have been no studies before which show that rotating waves can also be generated by pi/2 phase-shifted waves, which are not completely orthogonal with respect to each other. Oblique waves were necessary to generate the diagonal separatrices for the octopole vortex and force the waves to propagate away from the corners and towards the edges of the wave maker. I suggest that a similar modeling may be applied whenever pairs of counter-rotating vortices appear on every edge of an arbitrarily shaped domain. For example, in the small-scale polygonal wave tanks presented in the paper of Chen. Now, in obtaining the non-dimensional factor alpha, which rescales the Eulerian contribution for the octopole vortices, I described two methods. The first method obtains alpha naught, which gives the minimum peak in the normalized kernel density curves of the vorticity difference distribution. The second method obtains alpha naught, which yields the minimum value of the average vorticity difference. In the paper of Francois, the Australian team, they did not describe exactly how they adjusted the velocity field magnitude to match their experiment results. Here I have clearly outlined the two methods that I use. Now, since the obtained alpha naught for all cases of the octopole vortex were greater than 0, the Eulerian contribution indeed exists and is necessary to qualitatively describe the phenomenon. Also, since alpha naught for all cases were greater than 1, the Eulerian vorticity contribution at the interface always remains to be greater than the Stokes drift vorticity contribution, consistent with the prediction of Parfenev and the Russian team for the vortex lattices, where the prefactor is 1 plus square root of 2. The factor 1 is for the Stokes drift, and square root of 2 is for the Eulerian contribution. So the Eulerian contribution is always greater than the Stokes drift contribution. I am also the first one to show the vorticity in the liquid bulk for the vortex lattice. In previous studies, the Eulerian vorticity contribution at the interface had discrepancies caused by capillary and wall boundary effects. These factors were attempted to be corrected by Parfenev by considering the existence of a thin film at the interface. In my case, I have eliminated capillary and wall boundary effects by looking at the vorticity in the liquid bulk and at the center vortex cell of the 3x3 vortex lattice. The peak widths of the density curves of the vorticity ratio distributions encompass the analytical value without the Eulerian contribution, but the peaks and the percentile rank deviations themselves suggest that, although this is the case, the vorticity leans towards the analytical value with the additional Eulerian contribution. This shows that the Eulerian contribution indeed exists. I had lengthy discussions with Vladimir Parfenev himself, and we had the same thoughts about the additional Stokes drift-like contribution that the team of Nicolas Francois added to improve model experiment agreement, being the Eulerian contribution arising from the liquid bulk viscosity. My results also suggest a spiral pattern due to the absence of self-similar scaling of the vorticity ratio distributions for the center vortex cell, which provides additional insights for future analytical investigations. My experimental study opens the possibility of manipulating particles beneath the liquid gas interface and demonstrates how subsurface vortices can be studied further. This ends my presentation, and I would like to thank ASTH RDP Graduate Scholarship Program, Dr. Vladimir Parfenev, Dr. Sergey Filatov, Dr. Paul Fontana, and Dr. Washa for their help in the analytics and experimental procedures. And then here are my main references for this presentation. Thank you.
Okay, thank you, Alfred, for that presentation. Okay, so I now open the floor to the members of the examination panel. So, okay, who wants to go? So we have Professor Almoro, Professor Vega, Professor Villanoy. Okay, so you can start asking your questions. Alfred can answer Professor Soriano can interject at any point. Okay, so who wants to ask the first questions? Okay, Professor Vega.
Alfred, thank you for the presentation. That was very clear. I
Yes.
would say that the presentation was even a lot clearer than the manuscript. So you've outdone yourself. So I have a couple of questions. I just have to choose. Would you mind making me understand first off what the reservations, what the origin of the reservations of the first group was?
Well,
yeah, so I know theirs was a fudge factor. So they put a fudge factor in front of their Stokes drift and
yes.
left it at that. It was a phenomenological fit essentially.
Yes.
But then I don't get the principled objection to the other group's explanation that this may have been caused by a viscosity, for instance.
Yes, sir. So thank you for your question, sir. For the first group, for the Australian group, they thought that since the vorticity generation presented by the Russian group was a required nonlinear process, and they detected that their waves were linear, the contribution of the viscosity through the nonlinear generation of the vorticity as contributed by the viscosity can be neglected. Also, since the value of the viscosity of water, the liquid that they use, is in the order of 10 to the minus 6. So they assume inviscid flow. However, in my experiments, I detected that the Reynolds number is much less than 1, and I cannot assume inviscid flow. That's why they got their analytical results using the inviscid assumption was not enough to describe quantitatively their experiments. So I think that was the misunderstanding. So the waves that they detected were linear, and they did not believe that the Eulerian contribution due to the viscosity, which required a nonlinear process, exists.
Okay, thank you. What I don't understand though is what a detection of a linear wave is. I mean, linearity, as far as I'm concerned, is not something that's sort of detected. It's something that, you know, whether a process is nonlinear or linear. That,
yes, sir.
I mean, there is only one there's only one physics, right? So,
yes.
it's a matter of what approximation
Yes, sir. Yes, sir.
you use. So,
yes, sir.
I mean, given what you presented and you know what the state of the field was prior to me reading this, I would have concluded immediately that the Australian group was off. I mean, the working assumption was just a mistake. So I don't understand what you mean by linear waves being detected.
Well, that was what they stated in their paper. So they stated that this is different since the work of the Russian team is different because this requires a nonlinear process, while our waves are essentially linear, and we have waves with small wave steepness in comparison to the required waves for the process in the vortex generation of the Russian team. So I'm not sure. That's just what they said in the paper, sir. So I haven't asked them personally for their reason, but that's what I got from their paper.
Okay. Thank you.
Okay, more questions? Okay, Professor Almoro.
Right. Alfred, slide 47. Yeah. Yeah, so running the animation, it showed and even the labels, meron diyang radial velocity, no? So are we supposed to, what is the relevant feature there? Is it the radial motion or the wobbling, no, in the parang gyration? So which part there is the Eulerian component?
Yes, sir. So to get the, you see, when I compute the vorticity, I get the curl of the velocity field, but then I get the period average value. So the gyrations or the curling becomes irrelevant the drifting of the particles becomes the relevant contribution. So as I presented a while ago, you can look at the motion of the particles in the Eulerian and the Lagrangian views. In the Eulerian view, if you fix your view at a particular location in the trajectory of the particle, in some small region, we'll see that there's no mass transport. It just curls and curls all over every period. So if you period average that value, then the Eulerian contribution due to that motion is 0. Now, if we look at the Lagrangian view, if we follow a particular particle being advected by the waves, then we see that it drifts forward. So that net drift is what contributes to the vorticity, the period average vorticity. So saying that you have a Stokes drift contribution, so due to the waves, you have that drifting due to the waves, plus another contribution which is not due to the waves, but due to the viscosity.
All right, all right.
Yes.
So maybe related to that, you mentioned there that it's wobbling about the eye. So does the particle actually converge to a singular point that you consider?
No, sir.
Why?
No, sir. Well, if for the study of Chen, they observed that it depends on the wettability of the particle and the density property. So for my case, since I matched the density of the particles that I used with the density of the fluid, they are embedded on the surface or at the interface. So they follow the motion of the fluid parcels themselves. So they are not necessarily trapped or stuck on the eyes of the vortices.
All right. Maybe a quick related question. So slide 64. So you describe the ano ba tawag yan? Beneath, di ba?
Yes, sir.
Did you see any funnel? Because supposedly it's from the top, you will see the world, di ba?
Yes, sir.
And then from the side, maybe you can see like a funnel. No. Did you expect to see the eye or the funnel of the vortex from the side view?
From the side view.
Yan, kasi yung angle na yan, di ba? Side view yan, di ba?
Yes, sir. The first video, sir. This one.
Even yung photo on the left, yan. No? Photo na lang siya, screenshot. So, yes, do you expect to see some local regions where the liquid will look like the profile will be like that of a funnel?
If maybe, sir, if I orient the laser sheet sideways, but I'm not sure yet. I'm not sure if I can actually construct that, because creating a funnel requires the scanning of the laser sheet throughout the entire YZ or XZ plane. So I haven't tried that but that would be interesting in the next experiments.
Yeah, so ano na lang, maybe, so from your experiments, do you observe any region that you can consider as the singularity where the eye of the vortex is? Or it's just a general flow and the eye is somewhere there, but you did not actually precisely determine the location of the eye.
You cannot see it, sir, because it's just a sheet of particles moving. So and I can do an automatic tracking of the particles. So I need to post-process.
Yeah, but can you compute it?
Sir?
But can you compute it?
Compute?
The location of the eye.
I'm not sure yet, sir, if I can do that.
But you have a distribution of particles, and then you have the different velocities. can you, in fact, extrapolate from there a region where the eye is probably located?
Probably, sir, if I can get um, a thicker profile of the laser sheet. Yes, sir, maybe. But I haven't tried it.
All
I
right.
haven't tried it yet. Thank you, sir.
Others?
Okay, Professor Villanoy, do you have a question or
Yes.
questions?
Yes, yes. First of all, Alfred, congratulations.
Thank you, sir.
You have done a very impressive work. So congratulations to you and to your advisor.
Oh, thank you, sir.
So, so this is a bit unfamiliar to me because I usually work with much larger scales. No? So in your experiment, you mentioned that the waves that you generated are capillary waves. Tama yun?
No, sir. I used the gravity capillary wave dispersion relation, but the regime of the surface waves, the frequency, is in the gravity wave regime.
Also, it's in the gravity wave.
Yes, sir.
So in the question I wanted to ask was the things that we've shown here. If you scale that up to larger scales, bigger waves, wavelengths of the order of a meter, or even larger, where the Earth's rotation begins to take effect. What do you think would happen?
Well, thank you for that question, sir. In the paper of Orfeniev, they mentioned that this could actually be applied for surface waves in the ocean, but they did not cite exactly what paper shows this. But as I've seen in other papers, for example, in the paper of Garib, they detected horizontal vorticity for spilling water waves. And I think that's what contributes to the vertical vorticity as mentioned in the paper of Orfeniev. And the scale of the waves that they use are in meters, and their setup is in the scale of meters. So if I think this can be applied to larger scales, but with the Earth's rotation, there would be some additional factors that would affect the structure of the vortex pattern. I don't think we could actually observe in nature the order of the vortex lattice perfectly. So I think the theory of Parfeniev with the prefactor and the scaling with respect to the depth can be applied to much larger scales in waves with wavelengths greater than meters. But I think additional factors need to be taken into account, especially wind, for example, wind forcing and the Earth's rotation. So, but I'm not yet sure about that, sir.
Yes, because this has important implications also in the ocean because some internal waves, they result in the convergence of plankton, mga particles that they freely float in the water. So when we converge this, they tend to have biological interactions that can enhance the productivity. So it's very interesting if we can find applications in the ocean.
Yes, sir. Thank you, sir.
Okay, so before I ask my questions, let me remind the audience that they can also ask questions through the group chat. Okay, so Alfred, you have this structure with 8 separate recesses, right?
Yes, sir.
Is is there a way to invent a scheme that will yield a system with 16 separatrices?
Hmm. Well, scheme of 16. Yes, sir. I think
How will that happen?
if I use an octagonal wave maker, I think I think I can produce a system with 16 vortices using an octagonal wave maker. The same setup using um, cylindrical wave makers as edges, and then I create an octagon, and then I half submerge it and produce waves using that pattern. I think with my observations that I can produce counter-rotating vortices for every edge of the wave maker as seen in this octopole vortex structure. I think I can produce 16 using an octagonal wave maker.
Okay. And what do you expect to get if you have if the cross section is a pentagon?
So actually, sir, I've experimented before with other patterns, but
Yes.
the expression for the velocity potential just becomes more and more difficult to deal with. And for the pentagon, I tried, but I could not generate the same pattern with analytically. I could not generate the vortex pattern with 10 vortices or 5 pairs of vortices. In the experiment, I also have not seen it, but for the hexagon, I was able to see it for an experiment. I was able to produce 12, but it becomes difficult to express it analytically.
Okay. I mean, okay. Now, if you use, say, something with an elliptical cross section, I mean, the ellipse has this special focusing properties, right? What do you expect to see?
Well, for an ellipse, I've seen an experiment being conducted by the Russian group of Filatov in a JETP paper that they published, that they used a circular cross section or a cylindrical container, and then they oscillated the container. And after some threshold acceleration of this container, vibration acceleration, they were able to produce vortices along the sides of the container. With regards to the count of the vortices, I am not sure how many I can generate with a particular geometry that is close to a circle, for example, an ellipse, as you said. But I think you can still generate symmetric looking vortices with an ellipse. But for the longer side, for the major axis, the vortices will be larger in comparison to the ones closer to the smaller concavity. That's what I think, sir.
Okay. So the next question is just a due diligence question.
Yes.
So you used RK4 to construct particle tracks,
Yes,
slide
yes.
46. What checks did you use for your numerical, for the convergence of your numerical integration?
Well, for the particle tracks, I did not. For the particle tracks, I did not actually compare one-to-one the particle trajectories, because they do not really necessarily match, since asymmetries can be observed in actual experiments. So the only check that I did really was that second part of the study on the octopole vortex, where I measured the difference between the analytical and the experimental vorticities. With regards to the specific tracks, I did not check. I did not quantify the exact location of each particle. For example, if I use the velocity field for the experiment. So the only check that I did was the minimization of the minimization of the vorticity values.
Okay. My last question is, what happens if you use different liquids?
Mm.
Corn oil, alcohol, glycerin. Do you have to introduce new physics?
Well, I think for the case of the more viscous liquids, I think the surface wave damping will affect greatly the generation of the vortices, but I haven't studied that yet. The kinematic viscosities of water and the solution that I used are in the order of 10 to the minus 5 to 10 to the minus 6, or no, 10 to the minus 6 to 10 to the minus 5. So I haven't tried yet in the order 10 to the minus 3 for pure glycerin and other more viscous liquids. But I think the most relevant factor in the generation of these vortices would be the surface waves. So if I use a liquid that has greater viscosity, then the 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 dispersion relation will be modified, and the viscosity will affect the surface wave damping. So possibly from the wave maker, the waves will have decayed so much that it won't reach the other side or the other wall, so that you don't generate the standing waves. Same for the other wave maker on the other side. So you can't really generate a perfectly looking vortex lattice in that case. With regards to, for example, alcohol, I think the surface tension would be the most would be the factor that would affect the generation most. So if you change surface tension, then the requirement for K and omega using the dispersion relation changes so that you can generate the vortex lattice. So I think that's the only factor that will be relevant for those cases of other liquids.
Okay, are there other questions from the panel? Okay, so Ian, then Val.
Okay. So Alfred, also by the way, I want to remind the audience too that we are a multilingual institution. So kung magbinisaya mo, pwede. I'll translate it for the rest. I have a question here about so the underlying logic of your analysis rests on this Eulerian contribution having the same form as the Stokes.
Yes, sir.
That's a buried assumption throughout the entire analysis, your data analysis, and in fact your conclusions. But the manuscript doesn't actually have a clear accounting of, how that form came to be, because you essentially invoke Parfaniev's analysis, which I didn't read. So I'll ask you something about Parfaniev's work then. I mean, in getting that form, did he assume, the fully nonlinear equations for the water waves? I mean, did they work from an assumption of from within a nonlinear setting to get that expression?
Yes, sir. They started with the Navier-Stokes equation and a similar process that I used, but just a different notation. And then they included the viscosity, and in their paper they also included some surface film contribution. So they started with a linearized form of the Navier-Stokes equation, and then they found that there's no contribution to the vertical vorticity using that linearized version of the Navier-Stokes equation. You can't get a vertical vorticity or a z component of the curl of the velocity field, which contributes the overall vorticity field. So they extended that linear approximation to the second order in the wave wave steepness. So in that after solving in that level, second order assumption, they found that the horizontal vorticity, not so the horizontal vorticity that they obtained from the linear assumption actually sources the vertical vorticity, in the second order. So so that was their main result. So that is what contributes to the Eulerian contribution. Now they solved the Stokes-Drift contribution separately with similar to what I did. So for my case, I used UP, which is the envisaged assumption or the potential velocity field. I plugged into the mass transport velocity equation and then computed the Stokes drift. So they did the same. So after that, after getting the Stokes drift velocity, they then got the curl. And so that's the Stokes drift vorticity contribution. And then they merged the two contributions, the up to second order Navier-Stokes equation vorticity plus the Stokes drift contribution due to the waves. They merged that, and then some terms canceled. And then with the assumption of no existence of the film, which is the case for the previous study of Filatov in their PRL paper, they found that for the case of the orthogonal surface waves with phase shift pi over 2, which generates the vortex lattice, you can get those two contributions, wherein the Eulerian vorticity contribution was generated by the viscosity, but it does not explicitly depend on eta, the value of viscosity, because it gets cancelled out in another term of.
So it's sourced by. So the viscosity needs to be non-zero, and yet the viscosity never really appears as a free parameter in the end.
Yes.
Okay,
so that's what happens.
All right, so that answers my next question, which would have been, could you have used the discrepancies? Yeah, I mean, so you technically answered my next question, which could you have used the discrepancies between their model, with a free the idea was going to be if there is a free viscosity parameter in in their results, could you have used your experiments to independently measure viscosity and then compare it with the other reported viscosity that you have? Kasi diba, if viscosity is driving this effect,
yes.
then and you can measure the differences between this Eulerian contribution, I guess from the linear theory or from the Australian group theory, which is basically what you characterize now quantitatively, then you would have an independent measure. You could, in principle, have an independent measure of the viscosity, which you can then corroborate with a different way of another way of measuring viscosity. But you're saying this does not show up.
Yes, sir. It does not show up in the expression.
And yet it's essential to get the effect.
Yes.
Okay. Yeah, I have more questions, but I'll pass it to Dr. Sorry, Dr. Soriano.
Good job, Alfred. So he asked the questions now. So could you show the slides? Sorry, I lost track of that slide number where you have an image where you took the frequency average in XY. So you have some nodal points showing up.
Wait.
So it's an inset.
Slide.
So in that image, there's the stack also, but also there's the Fourier. Yes, there you go. There. Don't you think that the peaks here, because earlier Dr. Almoro was asking, can you find where the nodes are? Don't you agree that these are the nodes? And in fact, you can find the nodes using this technique. Right?
Yes, ma'am.
So Dr. Almoro, that may answer your question that the nodes can be found this way.
I was asking about the I.
Right? Isn't this the I?
No. I is a singular point. Is just a XY coordinate, not a region. So it's somewhere there in the blob, in the node, but it's a precise location
Mm.
baseline will emanate from.
Mm.
Hmm.
Okay.
But this is the point, like in storms, this is the point where there is hardly any movement, right?
The eye. The eye is where there is no movement, but this is a region where the speed is fastest.
Oh,
Oh.
is it?
If you look at it from the side,
Yeah, the funnel. Where's
yes.
the axis? Where's the axis?
Mm.
All right. Because correct me if I'm wrong, Dr. Villanoy, the funnel in a funnel-like structure, the eye of the storm is that point where there is no velocity, right?
There
That the
is there is very or low horizontal velocity, but you still have vertical.
vertical velocity, but no horizontal velocity.
Horizontal.
Thank you. Okay, my next question is, Alfred, since these are waves and waves come in different forms, so can you relate this to, say, other wave phenomenon like electromagnetic waves?
Yes, ma'am. Actually, I've read a paper about metafluid dynamics, and it relates the microscopic magnetic field to the vorticity and the electric field to the Lamb vector, which is the cross product between the velocity field and the vorticity field. And if you think about it, uh, the waves may be analogous to some current in a loop, and the vorticity generates is the corresponding magnetic field. But I'm not sure yet, ma'am. But that's based on what I just read about metafluid that relates fluid motion to Maxwell's equation. So I think
Sorry, Alfred. What are meta? Sorry, this is the first time I've heard about this. So what are metafluids?
You just it's a paper, sir. There's a paper that describes or relates the motion of fluids to Maxwell's equations. So in that theoretical framework, the microscopic magnetic field is the vorticity, and you start from that, and then you get some turbulent charge density, turbulent current density. It's a different framework of thinking about the motion of waves, the velocity fields, and the vorticity fields. So they termed that particular topic as metafluid dynamics. So yeah, I think that's what the answer to Jing's question.
Okay.
Thank you.
Yeah.
So yeah.
Muna.
Ay, sorry, si Val.
Ay, Val, sorry. Ay, akala ko
Nagawang kita ng
nagtanong.
question,
Val,
Val.
sorry.
Sorry.
Ito pala epekto ng pandemic. Ang daming tanong.
Hindi ko nakikita lahat ng 5 at a time lang nakikita ko eh. So kung
Okay.
minsan
Kailangan mong full screen.
okay.
So, Alfred, so ang na-appreciate ko, yung mga magandang features ng method is yung particle, mag-scatter ng particle is you were able to determine the position, yung gradient, yung spatial distribution nila, and not only that, yung temporal dynamics ng mga particles. No? So earlier I was asking about deriving quantities other than this, yung mga direct measurements, and then yun ni Dr. Soriano. So again, from these nodal patterns, dynamic live nodal patterns, can you propose a way to derive or compute the surface phase map of the vortex? Kasi nandiyan na yung amplitude, nandiyan na yung distribution in space. Can you extend it to determining the spatial phase? No? Kasi from that, you will be able to generate the phase line, the interaction of the phase lines, the location of the eye, and also yung directionality, clockwise or counterclockwise, yung vortex from the phase map. can you propose, can you suggest ways to derive or extend your method to well account for the phase map?
Mhm.
Alfred?
Well, I've seen in other papers that dealt with the imaging of waves, or they can measure the phase using a Hilbert transformation scheme, but I'm not sure yet how to use it to locate vortices or the direction of rotation. But I know that using Hilbert transform or even Fourier transform, you can obtain the relative phase. So I think I need to just um, I'm not sure yet, sir, but I think it's in the post processing
Yes.
only. After I've obtained the waves, the motion of the particles, and the velocities, I think it's just a matter of post processing. But right now, I don't know yet how I can obtain the necessary or the quantities that you want to obtain, so,
All right.
using the phase.
Quick question lang, Dr. Sigera, no?
Sure.
So, ano yung yung particle approach, yung isang method, may mga limitations siya, no? I suppose nagka-clump yung mga particles, etc. ganun. So, can you again describe why the need to introduce the yung Schlieren method, no? Yung free synthetic surface Schlieren. Bakit kailangan pa siyang i-introduce for the beneath the surface? And briefly, can you describe how it works? Kasi hindi mo
Yes, sir.
describe. Okay.
Sige, sir. Babalik ko po, sir. Slide 36. So, yung ginawa ko, sir, kasi the original paper was written by Frederick Moisey, which I also contacted before during my MS thesis. And I've written an article about this, where I use the free surface synthetic shearing method, or FSSS technique, to visualize wave resonances in nonlinear surface waves. So the introduction of a random dot pattern is necessary so that one can see the distortions caused by the lensing effect of the wave crests and troughs. So they act like convex and concave lenses for the random dot pattern. It needs to be random so that when you construct the correlation matrix during the particle image velocimetry in PIV lab, hindi nagkakamali yung method to associate a particular window moving to a different window for the next frame. See, if you use perfectly structured lattice with
Alfred.
Yes, sir.
Wala akong clear ako about using random trace
yes, sir.
particles.
Okay.
Ang tanong ko, yung Schlieren, you need to deform a refracting surface and then combine it with an undeformed surface. Di ba yun yung Schlieren, di ba? So why the need to introduce that detection method to characterize yung vortex?
No, sir. I just use the FSSS technique for the waves, sir, not the vortex. For the vortex, I used actual particles. I seeded the fluid with actual particles. So this technique is just for the waves, sir.
All right.
Yes, sir.
Thank you.
Thank you, sir.
Okay. Ian?
Can I go back to your measure of nonlinearity, beta?
Yes, sir.
So I know, so this is a proposed measure. And
Yes, sir.
as far as I can understand, it essentially measures how closely your average spectrum mimics the dominant frequency. No?
Yes,
so
sir.
if it's 80 is basically the same as AF, then you're
Yes,
in a some sort of linear regime. Whereas if basically more of the power cascades into the other harmonics,
Yes,
the
sir.
higher harmonics, then you have something that's more nonlinear. So my question there
Yes,
is, so you take a measurement 15 seconds after the beginning of forcing, according to your manuscript. Am I getting that right? So there's a 15 second, presumably that's because you want to get into some kind of steady state.
Yes, sir.
right? So uh, is it really steady state? I mean, I'm just concerned because
Well,
if this cascading of power from
yeah,
dominant to the
takes time.
subharmonics, it takes time. It actually does not
Yes.
approach a steady state, at least in theory.
Yeah.
It will keep on going. Eventually, it will become turbulent, right? So,
Yes, sir.
I'm curious to know what set the 15-second time scale,
Well,
uh,
it was.
and if you went beyond it a little bit, do any of your results change? Kasi crucial dun, di ba? Because you take 15 seconds and then from that you infer your beta. And beta is not really a driving parameter. It's not something that you use. It's not something you can tune. I mean, this is one of the difficulties of it. It's a very highly nonlinear system. So you don't
Yes,
have the
sir.
luxury of having this knob that you can tune. You don't have a beta knob that you can tune to get a corresponding alpha knot. You're at the mercy of everything in your setup. So what you do
Yes,
is
sir.
you run the experiment and then you find a correlation between your beta, which is an inferred quantity, and an alpha knot, which is another inferred quantity. So my general question of principle is, are those alpha naught versus beta curves reproducible? Are they characteristic of the system that you have, or do they reflect more the choice of the time at which you've measured everything?
Well, for my case, sir, I was limited by the. Well, I recorded at 120 frames per second, so the amount of videos that I can take without uh, getting a low battery with the camera. Well, I just set the 15 seconds just so after a minute, I assume that the waves have already reached steady state. So also, if well, the 15 seconds was arbitrary, sir. So it was my choice of for the starting point of the.
But you understand my concern, though, right? My
Yes,
concern
yes, sir,
is
yes, sir.
it's possible that your beta is not stationary.
Yeah,
If you
yes,
keep,
sir,
you
yes,
keep
sir.
all the parameters fixed and then you have a measure of nonlinearity, I suspect that beta, again, because of this idea of cascades, I mean, it's a very clever measure. I thought about it. Like, first of all, I didn't understand it at the beginning, and I had thought hard about it, and I think I understand it. And it's a very pictorial way of essentially, well, tama nga naman, the nonlinearity will distribute the power from the dominant to
Yes, sir, yes, sir.
driving to the rest. So it's a very clever suggestion. My issue is the time scale at which beta also changes. Hindi naman problema. I mean, obviously, if this is quasi-static and our time scale is significantly long compared to the relevant time scales of our our personal experiences, then we don't really care, right? If it's constant within a day, okay, fine, I'll accept that. But
Yes,
I
sir.
mean, was there an effort made to check what the time scale is for the evolution of beta itself as an inferred quantity?
No, sir, I did not. But I propose an experiment to check if this beta actually changes. Since for the figures in DNE here are these are average spectra. So in space, and then I got the spectra in time windows. So I suggest that to be able to see if this beta actually evolves in time, then you will have to get measurements of wave heights longer, during much longer time. So um, for now, I just did this because I know that for the nonlinear case, for example, in oscillons, for the very highly nonlinear waves, the frequency, the dominant frequency shifts to half the forcing frequency. So the value of A sub F tilde becomes very small compared to the value of A tilde T. So the beta approaches 1 for that case of the very highly nonlinear waves. So I did not do additional experiments to check if beta actually evolves, since, as you said, there's transfer of energy, there's a cascade of energy in time. So for this experiment, I just set the fixed duration and then
Okay.
compared it.
Professor Almaro has a question.
Yes.
Alfred, yung sa title, Eulerian vorticity on and beneath surface waves. So from the title, and then all throughout the manuscript, so you're referring to the vortex. So my question is, since di ako masyadong familiar sa mechanical vortices, how do you categorize this physical effect? Pwede ba siyang swirl or eddy current? Bakit kailangan tawaging vortex? Yun yung question ko. Kasi hindi ko nakita yung funnel eh. Yun yung definitive na feature, di ba? Meron pang eye. So ito may blob. It's somewhere there.
Yes,
Pero
sir.
pwedeng umiikot lang, nagsisirculate.
Yes,
So
sir.
can we not call it a swirl or a whirlpool or something?
Well, I just used it because it was the term used by the Russian team in their experiments. Also, sir, I've read that well, if you use eddy, there's an assumption that the background flow is turbulent. So there's a cascade of energy between these eddy sizes. You start with the largest scale of eddies, and then after some time, the energy of the largest vortex becomes distributed to smaller vortices. Then you get a cascade, and then you get the Kolmogorov spectrum of turbulence. And then for vortices, I think it's more that there's no requirement that you transfer energy between these vortices. In contrast with the term or when you use, for example, eddies and eddy current. So that's why I use the term vortex, because first they termed it vortices in the previous studies, plus this that I cannot use eddies because the background flow is not necessarily turbulent.
All right. So I guess my suggestion would be to put it somewhere at the beginning.
Yes.
Yung terms, kasi kapag vortex, for example sa mechanical vortex, ang visualization is meron niyang eye. And then in optical vortex, yung intensity 0. Phase is undefined. So merong ganong definitive features.
Yeah.
So therefore kapag Eulerian vortex, may hinahanap, well ako may hinahanap, pero the way you explained it is meron siyang parang jargon na yun yung context ng
yes.
Eulerian vortex. Dr. Vega?
No. It's Professor Villana first, and then
can I just? No, I have a comment lang on the question.
No, Ian. It's Professor Villana muna.
No, it's a comment on the question kasi.
Yeah, pero dapat nauna siya kay Val eh.
Sige lang. Go ahead.
Hindi
Sige
kasi
lang, go ahead.
yung
Okay, sige. Go na.
historically kasi for any vector field, its curl is always its vorticity.
Yeah.
So, I mean, there are contexts in optics and mechanics, but when you're taking the curl of your vector field, your velocity field, it is rightly vorticity.
Yes.
In fact, so that's my comments. I'll say my.
Thank you, sir.
Okay, Professor Villana, I think you raised your hand previously.
Alfred, you showed a slide of a vortex cell where you have the particle movement.
Yes, sir.
Yung sa lattice yata yan.
Yes, sir. Wait lang. Slide. This one, sir.
Yung nakikita yung individual particle movement. You may gyrations.
Yes, sir. This one?
No.
Yan.
No.
Oh, anyway, we can use this. Yung diameter nung orbit ng particle, does it change as you move away from the center of the vortex?
I haven't actually quantified this, sir, but based on my experiments, I saw that when you move down, the orbit diameter decreases. But I haven't actually quantified, nag-plot ako ng particle diameters because it's hard to actually measure this because you need to actually construct the particle trajectories and then get the profile of the radial profile of the diameters of the orbit. So I haven't actually checked, sir. But I think since the particle tracks becomes more stretched close to the separatrices because you increase your velocity, I think the orbit becomes more elliptical and less circular, so I can't really define whether the diameter becomes less as you go towards the boundaries. So
Doon sa slide, ano ba yun, 38 pa yun, yung tiningnan natin kanina?
Yeah.
Yung sa octopole.
Yes, sir. Yeah.
It seems na mas yung diameter ng gyrations mo increases as you move towards the sides. Dito sa upper right.
Diameter, sir.
Oh.
Mas parang nasa stretch yung observation ko lang, sir, parang mas nasa stretch yung particles kasi dun sa reconstruction ko parang ganun din yung na-observe ko. Mas nasa stretch, for example, dito.
Dito.
Sa side compared dito sa loob. Pero kasi sa octopole vortex to, sir. So, hindi ko sure sa vortex lattice din kung ganun din yung case niya. Pero hindi ko na actually siya talagang in detail na inaral kasi medyo mahirap yung comparison. Yung exact comparison.
Kasi ang gitna dyan, yun yung node mo. That's where you have your minimum vertical displacement, di ba?
Oo.
Yung gitna niyang mga vortex.
Yes, oo. So mas maliit yung orbits. Mas parang compressed siya while doon sa separations mas stretched yung orbits. Yun yung medyo observation ko lang.
And how does this hindi ko masyadong nakuha yung when you looked at the subsurface eh. How did it change compared to the surface?
Well, hindi ko kasi zoom in, sir, pero mas maliit yung orbits niya compared dun sa surface. Yun lang yung na-observe ko. Plus, yun nga, since na-measure ko naman yung vorticity, kung paano siya nagde-decay, yun nga, nagde-decay yung vorticity as you go with depth. Yun lang yung comparison na ginawa ko with regards to...
At saka ang orbital path ng particles sa ilalim, palalim from a linear wave is nagde-decrease in diameter.
Yes, sir. That's what I observed.
Okay, thank you.
Thank you, sir.
Questions from the audience? Okay. Sige, Ian.
Yeah. Tuloy ko lang yung comment ko, sorry kanina. Kasi ako yung turo ng 231, 232 sa kanila eh. So dapat alam nila yung curl na.
232 lang, sir. 232 lang, sir.
232 lang, sorry. Excuse ko na si Alfred. So, yeah, ang isang ano ko ay it's very similar to where Dr. Almora was coming from. In my case naman, I was having a hard time trying to understand the significance of the use of vorticity as the main observable in this study. So, I mean, para siyang, in some sense, the vorticity here is really nothing but a surrogate for the velocity field. Right? So,
yes, sir.
So would you say that the vorticity, again, this is how it's similar to Dr. Almora's question, is essential as a concept in any of this? Or could you have focused entirely on the velocity field?
The vorticity is essential, sir, because you see, if you look at the velocity field, you will get a contribution of the fast gyrations. But if you look at the vorticity, the period average vorticity to be exact, you're looking at the slow drifting, which is contributed to by the mainly by the Stokes drift and the Eulerian drift contribution. So these two contributions are slow drifting contributions. So if you look at the velocity field, then you will have, for example, sa ginamit ko, UP, pag in-integrate mo siya, makukuha mo yung drifting plus yung gyrations. So, since yung gusto lang na i-observe natin is yung drifting kasi yun yung na-observe na doon na-observe nila Francois at nila ng Russian ng Australian team and ng Russian team na may additional contribution doon sa slow drifting, hindi doon sa gyrations. So, I think kaya lang vorticity yung ginamit nila kasi para diretso na yung slow drifting contribution yung natitake na check, hindi na kailangan ng curling.
Okay,
Yeah.
so this would be a nice discussion in the manuscript. I think I agree with Dr. Almoro. Just to,
Okay,
to
sir.
point this out,
Yes, sir.
kasi when you say when you use a concept such as vorticity or a vortex shared across different fields,
Yes, sir.
it's helpful to highlight the special role that it plays in the entire study. Kasi otherwise, like I was confused on bakit nga ba vorticity, when in fact maybe you could have just focused on the velocity.
Velocity.
So
Yes,
I
sir.
think I get your explanation. Thank you.
Thank you, sir.
Magpe-flex din ako. Estudyante ko yan si Alfred. Magaling yan eh.
Ako magpe-flex. Ako unang nakakilala dyan. Hindi. Actually, yung mga high school teachers niya, tsaka principal yata nila sa Southern Mindanao campus, pineflex niya na siya yung math teacher ni Alfred. Okay. Questions from the audience? Okay.
Wala na akong tanong.
Ako wala na. Audience?
Kung walang
Meron bang
I'd just like to congratulate Alfred.
Yes,
sir.
Okay.
Thank you, sir.
Meron bang nag-check ng live stream? Baka may tanong doon.
Wait. Let me
Wala.
check. Wala.
Pwede naman sila mag-zoom, dapat dito sila nanood.
Okay. Sige. Okay.
Wait, just to remind everybody that Alfred was one of our first, Perry, is it correct? Summer
Internship.
Yeah.
from
Sabay-
high school.
Yes, sabay
SMB
sila
camp.
sabay sila ni Damien tsaka ni sino nga ba to? Yung advice ni Eric.
Art.
Saka si Rich kaya lang nasa ibang group.
Yeah.
Wala sa physics si Rich eh. Basta yung ibang groups, di ba? Di ba, Nat? Yung atin yata yung hindi masyadong masaya eh.
Oh, but Alfred won the best poster, I think.
Okay. Sige. Okay, I think we can adjourn. Ian? Oops, teka. May
May tanong si Rich.
Break ba tayo?
okay, last I think. Okay, mukhang may
Meron
nagtanong.
pa akong tanong.
From Rich. Okay, pwede isingit ko muna sa to kasi nag-solicit ako eh.
Sige, yeah.
From Rich. What's the limit of the particle size that you can track? What dictates this limit? Even if minimal, isn't there some sort of optical distortion that's being introduced to the system depending on the camera lens, the settings that you use? How does this affect your experimental results? Note that this may have a noticeable effect for smaller scale experimental setups. Okay. Slide 50. Why choose those values for beta?
Hindi niya pinili yung beta, yun yung point kanina. Point ko kanina. He doesn't get to
Anyway.
choose. He doesn't
Anyway,
get to choose beta.
Yeah. Anyway, yung optics question na lang ay yung optical distortions question na lang siguro kailangan i-address.
So, prior to processing naman, sir, nagka-calibrate ako ng camera for distortions using MATLAB. So, every start na bago ko i-feed sa PIV lab yung data ko, pinapost-process ko siya such that ma-remove yung distortions ng camera lens. Tapos, with regards to yung sa minimum particles, usually kasi ideally, i-weigh mo kasi yan kung ilan yung particles na gusto mong ilagay. Kaso lang kasi sobrang liit ng system ko na I needed to do multiple trials to get the optimal number of particles. Tas na blood detection ako, and then I checked na dapat within the range of number of particles per interrogation window na mag-yield to the smallest error based sa Ph.D. thesis ni William Thillick, yung author ng PIV lab. Yun yung ginamit ko na yun yung ginamit ko na interrogation window for the PIV. And meron din akong error analysis ng PIV ko sa MS thesis. So hindi ko na siya sinama actually dito. So yung best results ko na lang yung sinama ko dito sa thesis. So I think sana na answer yung question, Eritz.
Okay, maybe we can thank Alfred.
Di pa, may tanong pa si Ian.
Ay, may tanong. Sino pa may tanong?
Ian.
Pasensya ka na,
Ay, sige, Ian.
Alfred. This is a indication that you've given a great talk and it's a great topic. It's a great topic. Hindi ako diba? I mean, the opposite would be true. If nobody were asking, then it's a boring, everything else is negative. So yung ano lang, it's just a comment. So I had a comment about beta. I also have the same comment about alpha naught. So I worry about the veracity of your conclusion simply because it's not clear to me that any of these quantities are time independent.
Yes, sir.
So it at the very least for this dissertation, maybe that should be put as a comment, opening the door that this, in fact, I mean, testing whether this is stationary. These configurations are already stationary at the time of your observation. Needs to be done. Kasi marami, hindi lang siya sa beta, hindi lang siya alpha naught. Right? So
Yes,
concern yun. And then yung final comment ko really is, again, it's important to flesh out in a dissertation the underlying logic of your analysis, and one of which is the form similarity of this Eulerian contribution to the Stokes grid. Kasi if that, if there was something else that complicates that, for example, if the form were not the same, if the surface structure was not the same, well, first of all, the analysis would require something a whole lot more complicated.
Yes, sir.
And everything that you said will be wrong.
Valid.
Will be invalid, right? So malaki kasi yun eh. Hindi lang yun siya. I mean, there are many impressive measurements that were made. The experiment is very impressive, but in the interpretation of your results, those things kasi really rest on very big assumptions that really need to be articulated in the dissertation.
Okay, sir. So include ko na lang ba, sir, yung explanation ko about dun sa kung yung sa theory nila Parfenev?
Yeah.
Yeah. So. Plus yung vorticity.
Vorticity, that's also Dr. Albora's comment. Tapos yung beta and alpha naught na dependence on time.
Yes, sir.
It's just an assessment of the time scales. I mean, these things I would expect evolve. The question is whether the revolution time scale is much longer than relevant. Kasi kung di ba, kung practically constant naman sila, then we don't really care. Then everything is okay. Pero di ba?
Pero hindi ko kasi sure, sir, kung paano ko ma-calculate yung evolution ng beta kasi sa experiment si sir. So
hindi ba pwede parang, di ba kasi 15 seconds yung hinintay mo? Hindi ba pwede parang maghintay ka ng konting tagal? Di ba? So if you just change the time scale that you've mentioned, which is 15 seconds, would you see a change? I mean, I'm not suggesting that you do experiments, further experiments for this dissertation. It just has to be mentioned somewhere. This would be interesting to look at.
Just
as a sanity check for whatever you're concluding.
Sir. So pwede bang mag-mention na lang ako ng parang experiment na pwedeng gawin?
Yeah, para din sa grupo so that they can check themselves if you don't want to check it anymore.
Hey.
Okay, I'm done. Sorry.
I'm done.
All right.
Right. Dr. Esguerra.
Okay.
Hello, Dr. Esguerra.
Yes.
Before we close, let us not forget to have a family picture. A group
Well,
picture?
I have kept, okay.
Could
Yeah,
you stop sharing your screen, Alfred?
Yes, ma'am.
Thank you very much for your presentation. And then let's have a gallery view.
sandali lang ah. Sandali lang, sandali lang.
Please, all those present, if you could kindly show yourselves, please, so we can have a
Paano ba ginagawa yun?
green
Ala,
screen.
hindi naligo si Nat.
Sandali lang. Paano yun?
Screen? Green screen?
Yeah,
Sige.
yeah. De, pwedeng sa side mo na lang, medyo nahihirapan ako eh.
Yes, okay, green
Okay,
screen.
yung ibang pictures na print screen ko naman kanina, kita ba ako?
Yes, kita kayo. And yung iba, if you could, ito na ba? 16? Yes. 16
Damian,
months.
D.
This is all there is. Okay. Again, print screen. One more print screen. Smile for the camera, please. There we go. Thank you very much.
Okay,
Thank you.
bye.
Thank you.
Thank you, Alfred. Well done.
The committee will have to, ano ba to? We'll have to deliberate, but congratulations,
Yeah.
Alfred. We have to, paano ba to?
Lilipat ba tayo ng...
Yes. Gumawa ng Zoom meeting si Dr. Vega for deliberation.
meron ba?
I'll send you the link in just a bit.
Thank you.
Saan sa Gmail?
Sa Gmail yung lahat.
Oh, sige, check ko.
Sige, sige.
Okay.
So within 5 minutes, dun tayo.
Okay.
Okay, sige. Thank you, Alfred, ulit.
Thank you
to
po.
everyone.
Leave na ako ah. Okay.
Thank you po.